Hello, I'm Yongchun. I present gesture authentication for smartphones, evaluation of gesture password selection policies. The work was collaborated with Yongwan Shin, Junho Ho, Professor Hyung-Sik Kim, and Professor Ian Oakley. Many researchers believe the use of gesture as a password method has the potential to improve security and usability. While existing studies explore gesture in a diverse aspect, there is no formal and standard framework to evaluate the security and the usability of gesture passwords. In this work, we provide systemical method to evaluate the security and usability of gesture passwords. How do people commonly select password on their phones? Many smartphone users choose easy-to-guess passwords for pins and patterns to lock their devices. It can be dangerous in security aspect when a malicious user is trying to unlock a valid user's device. A study actually shows that an effective password guessing attack on pattern can guess up to 32.55% of the dataset with top 20 probable patterns. Secret-based authentication such as password, PIN pattern is still needed even when you're using biometric authentication method, as secret-based authentication must be used upon device reboot and if a user fails certain number of unlock attempts with biometric authentication. Gesture password is a hand-drawn graphical password for smartphones. Gesture password can be a secure and usable option for touchscreens, as the number of possible gestures is large and info may require less attention to the screen. However, gesture password is not explicit in terms of recognition. This is because gestures are matched based on similarity measure, such as distance. And setting different thresholds for this measure would yield various results, and it is quite ambiguous to assess the performance of gesture password. Moreover, gesture password has a large theoretical password space, but available gesture studies collect a small portion of the space. We need a large gesture dataset to quantify security and entropy of gesture passwords. So based on the figure problems with gestures, we will explore gesture password security in the first study. Large gesture password dataset is captured, and real-world usability of collected password is assessed. Then we develop security evaluation metrics and attack methods. In order to collect a large gesture dataset, 5 steps of gesture password collection study are designed. Users initially create and confirm their password gesture. To make sure whether user success or fail to confirm their entries, dollar and protractor is used to measure similarity. It measures inverse cosine distance to measure similarity between two gestures. We then ask participants to guess other gesture by attack gesture creation and confirm step. We designed this step to distract users' memory before record step. Users finished the study by recalling their password gesture. The study was deployed on Amazon Mechanical Turk, and in total, 2,594 valid workers participated or experiment. We collect up to 13,000 final gestures with 20,000 log gestures. We collect a large gesture dataset, which is 5 to 25 times larger than prior gesture datasets. The usability of collected gesture password is assessed. Password setup and record time differ between recent gesture literature and our usability data. But our data is not directly comparable to prior gesture study, as we allow only single stroke on small size canvas as one lock method, while prior study considered multiple strokes and multi-finger approach as password. Comparing to online pattern usability result, we observe roughly similar setup and record time. We observe recovery rates are affected by creation and confirm of attack gestures. When user success attack gesture confirm, They are likely to fail recalling password gesture. A probabilistic model, Engram-Markov model, is used for effectively estimating probability distribution of gesture password. The major issue building Engram-Markov model arises. How do we make a gesture password just as a text password? We design gesture discretization step to solve this. Starting with each user gesture, we first simplify gesture with double-spectral line simplification method. We then separate the simplified gesture into substrokes. Each substroke is classified into angle and length ranges. In this example, it is divided into 2 length and 4 angles. Symbolic representation of substroke is generated based on angle and length classes. We reconstitute strokes based on class midpoints. The strokes are reassembled into symbolic version of gesture. Varying model parameters, 570 different bigram models are generated. To reduce possible error caused by discretization, we optimize angle and length classes with boundaries detecting edge cases. The best angle mark model is selected on 3 criteria. The first criteria is accuracy. We generate top 20 probable gesture from the model and correct test set to evaluate how accurate the model estimates user's gesture. The second criteria is fidelity. We reassembled symbolic version of our gesture and evaluate the similarity between the symbolic version and original user's gesture to see fidelity of our discretization design. The final criteria is coverage. The coverage evaluates the completeness of Ngram model by observing possible Ngram cases. With these selection criteria, the best performing model of 10 angles and 3 lengths with optimized boundaries can be defined. It can be observed from stroke distribution of the model that users tend to choose rightward and downward strokes initially, then short stroke for the center, and rightward stroke for the final strokes. We calculate partial guessing entropy and convert to bits of information to compare strength of gesture password space. We found out over diverse portion of password space, the gesture outperform pins and patterns. The result implies potential strength of gesture password. And we note steep increase in guessing entropy of gestures at lower alpha level. This would imply the weak subspace. Many simple forms of gesture are rather easy to guess, while complex gestures are more challenging to guess. So along with large gesture data collection study, usability and security of gestures are assessed. The next goal is to create novel authentic method for gestures. Important assumption for authentic method is the online attack scenario, where a malicious user who does not carry prior information about gesture have limited chance, let's say 20, to guess valid user's gesture. It is difficult to use available dataset to choose good representatives. However, discovering common gesture class and extracting optimal representatives are not new questions. We assess the security of dataset against the dictionary attack with 5-fold cross-validation process. 2 recognizers of the line protractor and dynamic time warping are used. To compare results in a diverse way, we set a wide range of thresholds for those recognizers, normalized in terms of false rejection rate. We correct tested gesture with dictionaries and describe proportion of successfully guessed gesture in terms of correct rate over a wide range of false rejection rate threshold. The online dictionary attack shows high effectiveness, guessing between 50 to 60% of gesture and equal error rate threshold of each recognizer. Comparing the value to threshold level of 11.54%, which corresponds to a distance threshold used in prior gesture work, gestures are guessed between 31.5% for projector and 23.1% for dynamic time warping recognizer. This is comparable to crack rate of pattern study, which achieved 33% in a mechanical Turk study. From our gesture password collection and analysis, we figure out that gesture password is a potential password scheme in terms of usability feature, such as the record entry time and security feature of high partial guessing entropy values, beating other password methods at diverse portion. However, not only the steep rise in partial guessing entropy at lower alpha, but considerably high level of crack rate against dictionary attack imply weak subspace of gesture password. A large proportion of users actually choose to use rather simple gesture for their passwords. So in the second gesture password study, we consider way to improve security of gesture password. Password composition policy may enhance computer security by encouraging users to employ strong passwords and use them properly, such as enforcing users to fill minimum password length, banning items, mandated use of symbols, or using multiple characters. The password policy can be enforced or optional depending on password policy designs. Two policies are designed for gesture password in our second study. No lexical policy, or word shadow in this example is displayed to inspire users' gesture. We provided open-ended guidance toward diverse gesture creation from users. Users can update the word freely on their own, and to construct the word dictionary, we use monosyllabic and disyllabic word set rated for imageability. For the blacklist policy, we create dictionary composed of representative gesture from the top 20 clusters derived from prior online dictionary attack study. We have presented these to participants and informed them they cannot use this gesture as their password. We also designed consolidated blacklist policy by merging similar gesture clusters together and creating top 20 dictionary. For gesture password policy design of three new policies and baseline policy, which is the same condition from the first study, ran online. We collect 1,000 participants per policy, 4,000 in total on Amazon Mechanical Turk. A text gesture creation step is replaced with typical card flipping memory game. On the first day, participants create, practice, get distracted, and record their gesture password. And they get invitations through mail to record the gesture in the second day. We then assess the gesture policy design on usability. After changing a text gesture creation to memory game, high record rates for both day 1 and day 2 are observed. We observe the increase in setup time and day 1, day 2 record rates on newly designed gesture password policy compared to the baseline. This can be interpreted as more participation involved creating while setting password. We also observed that whereas reduction in day 1, day 2 record rates compared to consolidated policy, which enforced users to create unique gesture the most, this is less than about 3% reduction from the baseline condition. Now we calculate partial guessing entropy with optimal angular Markov model constructed from the first study. The angular Markov model suggests the policy improved partial guessing entropy compared to the baseline condition. And it is interesting to note that lexical policy begin with lower guessing entropy than others, a small portion of password space, and ends with higher figures than others. This variation is possibly originated as the minority of users engaged strongly in lexical condition and created complex gesture passwords, making it difficult for an attacker to guess the full space of the set. On the contrary, all users in the blacklist conditions are enforced to avoid common gestures, so this reduces weak subspace of guessable gesture of low portion of password space.
and this leads to the increase in guessing entropy over diverse versions.
Now we compare results from online dictionary attack over new policies. We used the same method to find representative dictionary gesture as the first study. The lexical policy does not improve security against online dictionary attack, increasing crack rate over diverse threshold level. Comparing crack rate to previously reported 11.5%, the crack rate was 22% for baseline and 34% for lexicon. This is roughly 55% of difference from the baseline. Blacklist policy improved security against online dictionary attack. The crack rate was 15% for consolidated blacklist policy and 17% for blacklist policy. And this is roughly 23 to 31% difference from the baseline. To summarize the presentation, gesture passwords are a feasible authentication system. Input technologies and recognizers are mature and robust. People select predictable and guessable gesture passwords. The large possible password space does not always result in highly diverse gesture password set, and gesture password policy can help resolve this problem. Thank you for listening to my presentation.